So let's make sure everybody's cool with the position time graph, because if that's wrong, everything is going to be wrong. So you've got your amplitude, which is probably something around 5 centimeters. That's typically where your amplitude is, okay? So you're going to start up here, and you're at the top of that oscillation, and then it's going to come down like this. And so you're going to complete 2 cycles until you end up back here, okay? So this is going to be one period, that's going to be the second one. So if this thing is oscillating back and forth, that's what that thing's going to look like. So if that's wrong, everything else is going to be a train wreck from there on, okay? So think this through in terms of what's taking place. So you have that mass that's at the top of the oscillation. It's going to begin to fall, and as it falls, it's going to speed up, right? So as it speeds up, it's going to have negative velocity, because we're defining down as being a negative value. So it's starting at the top, and it's going to fall. Okay, right. So right away, what's the sign of my acceleration when it begins to fall? Positive or negative?
Negative.
Negative. So up at the top, my velocity time graph is going to start at 0. And again, there's 2 different ways you can think of this. You can think of it mathematically and go, oh, the slope of this tangent line up here at the top is 0, and the slope of this tangent line gives me my instantaneous velocity. That's a horizontal line, so my velocity is going to start at 0. So if you're a math nerd, you can go with that route, okay? If you're really a math nerd, you take the derivative of this equation. At that point, you're going to get a value of 0, okay? But you have to be really hardcore math nerd to do that. The other thing that some people like to think about, they just like to think of the physical situation. Oh, it's starting at 0, okay, because it's at the top of the oscillation. So anytime, this is going to be important later on, anytime that velocity is 0, that means you're going to be at that maximum amplitude. Whether you have a positive maximum amplitude or you have a negative maximum amplitude. That's also where you're going to be storing the maximum amount of potential energy, okay? And in this case, since you're at the top of that oscillation, because we're oscillating in a vertical gravitational field, at that top, that's going to be the sum of your UG and US. As it falls, you're losing UG because it's falling, but you're gaining US, but you're also gaining kinetic energy. So at this point, when it crosses through the midpoint here, this is when you're going to have your maximum velocity. So when this is here, at this point, okay, that position is crossing that equilibrium point. That's that middle ring. That's when you should have your biggest negative velocity down here. So this is where you want to think this through and go, okay, the position time graph is going to drive my velocity time graph. So what I'm going to look for is that when this position time graph crosses through 0, that's when you should have your maximum negative velocity, okay? Because that's where that's going to happen. It's going to be negative because it's falling down, and that's how we define this system. Now, if you look at what's happening in terms of your acceleration time graph, okay? So on your acceleration time graph, oh, I started with 0 velocity, and I'm gaining negative velocity. The only way that can happen is if my acceleration and my velocity have the same sign. Oh, I'm going to have some negative acceleration, so I'm going to start with a negative acceleration here, and then eventually that acceleration is going to go to 0. So that acceleration is going to go to 0 when your velocity is at a maximum, and when you're at the equilibrium point in that oscillation. So the reason that you're going to have maximum acceleration at that point is that's when you're going to be at like that equilibrium point. That's when the forces between the net forces are going to balance out. So you're going to have this big maximum acceleration, then it's going to go to 0, and then it's going to go like this. So these are going to kind of be like mirror images of each other. So you're going to have a a big negative acceleration, which is going to get smaller. It's going to go to 0 at that equilibrium point, and then your acceleration is going to go positive. Once it starts back up, you're going to have a smaller positive acceleration. It's going to go to 0, and then you're going to have a negative acceleration. So this, if you think about it, this velocity is always changing. Your kinetic energy is always changing because of the fact that you always have an imbalance of forces unless you're at the equilibrium point where everything is going to be at 0. So when you get to question number 12, is that the question you're asking about? 13. 13? Oh, I was looking at the wrong one.
Let's do like the 3.5 here. 13.
So question 13, if you make the amplitude twice as big, what impact would that have on Vmax?
Oh.
So here's the deal. So if you look at how you calculate Vmax, right? Vmax is 2 pi frequency times your amplitude, okay? So, and hopefully this makes sense. If you look at this in terms of a bigger concept, okay, so I'm going to step back from this equation for just a second. So if you look at period, which is 2 pi times the square root of m over k, okay? So what's the only thing that affects the period of that oscillation? What are the only two things? Mass and the spring constant. Is the amplitude a factor in this equation? No. So whether I make that thing have a very small amplitude or if I have it make it bigger amplitude, it's going to have the same value of period. Now, remember, period and frequency are inverses of each other. So what you can do is sit here and go, okay, well, if that's the case, then 1 over frequency, right, which is going to be the same thing as period, is going to be 2 pi, and then we're going to flip this over and have k over m. So frequency is going to be the inverse of that. And then you can flip that over and then you get units of 1 over seconds. So here's the deal. Whether you're talking about period or frequency, here's what I want you to see. Period or frequency isn't impacted by the amplitude. That's going to stay the same. But amplitude does impact your maximum velocity. Okay? So if you look at this in terms of a pure mathematical situation, so I'm going to say, okay, I'm going to make the amplitude twice as big. What impact would have Vmax assuming the frequency was constant? We assume the reason that we assumed that the frequency was constant was because amplitude isn't impacting this calculation. That's why we can say that. Oh, okay. So look at this. So this number here, as long as it's the same spring, as long as it's the same mass, everything here is going to stay the same. This number isn't going to change. So basically, this is like a constant multiplied by an amplitude. If you really want to get fancy, this is a linear relationship. Oh, go away. I have no idea what I just did. That's weird. Okay. So if you look at Vmax equaling 2 pi f a. This is y equals ms. It's a linear function. Because this is just going to be some constant based upon the spring. This is going to be your Vmax. So if you were to graph this thing, and if you were to put amplitude on the y-axis and Vmax here, first off, is that going to start at 0, 0? Yeah. Why?
No amplitude.
Yeah, if you don't have any amplitude, guess what? You're not going to be any velocity. It's just hanging there. Okay, well, that's fun. Let's watch this lab. Okay? It's like trying to talk to a freshman. So, if you double, since this is going to be a linear relationship, okay, because your 2 pi f is a constant, and that's what the slope of that line would represent, would be 2 pi f. So, if you double your amplitude because it's linear, what's going to happen to your V max?
Double.
It's also going to double.
Okay, but I have a question about that. I was like explaining with potential energy and kinetic energy. So potential energy we get doubled, right? Because the amplitude, like the H is doubled.
But you also have the spring energy in it. Okay, so here's how I want you to get out of that. Is that the reason that you're going to have more V max is because if you have a bigger amplitude, you're going to store more potential energy in the system. As you store more potential energy in the system, then you're going to have more kinetic energy when it crosses through that equilibrium point. Okay?
But like the potential energy is going to go by a factor of 2, the kinetic energy is going to go by a factor of 4.
Yes, because it's 1/2 kx squared.
But where does that energy come from? When potential gets doubled?
Because you have two types of energy. You have us. The reason where that comes from, your us in there is 1/2 kx squared. So that's where that other energy, you're just focusing on the gravitational potential energy, but you're also going to have energy stored as us. And that's where that comes from, is that energy stored in that x value. Okay. Yeah, you were just thinking in terms of but remember you also have us that goes with it.
Okay.
Okay? So that's, and we'll talk about that today actually.
Okay.
All right. Are we cool on that page?
Yeah.
Everybody cool? You got the graph, I can find your slope. We're good. Okay. Going once, going twice. Now, don't hand that in. This is, we got like, this is section 1 of 3. Okay? So don't hand it in. Just hold on to it. Stop that camera for a second while I hand out the next part. All right. So now we're going to look at how all this thing kind of fits together mathematically and conceptually. And I want to show you like a couple of different techniques you can use to solve these problems. So, got lavender sheet. These questions are going to be going off of the graphs that you just did. So you might have that, you might have those graphs open. Okay. So, number 1, and basically we're going to work, like I said, we're just kind of going to work piecemeal this together. Okay. So, what's the net force acting on the system at a quarter t? So, at a quarter t, what's your acceleration?
0.
0. So force net equals mass times acceleration. So if your acceleration is 0, what's your net force?
0.
0. Again, we're not saying that there aren't forces acting on the system. We're just saying that the net force is going to equal to 0. So when you look at that, so here's this oscillating spring. You're at that equilibrium point. What are the two forces acting on that system? Paige, what are the two forces?
The gravitational, or not
Yeah?
the gravitational force and the spring force.
Yeah. Okay. So because it's a 1.5 Newton or 1.5 kilogram mass, oh, that's 14.7 newtons. So basically, what we're saying is that at that equilibrium point, I'm not saying that there aren't forces acting on the system. I'm just saying that all the forces add up to equal to 0. So I've got a downward force of gravity of 14.7 newtons, and I've got an upward force from the spring of 14.7. They balance each other out. But once it crosses that point, okay, once it crosses that point, which one's going to, on the way up? On the way up, once it crosses that equilibrium point, what's going to be bigger, gravity or the force from the spring? Spring. Okay? On the way up, once it crosses that point, which one's going to be bigger? Gravity's going to be bigger, right? Because that spring is going to be less and less compressed. On the way down, when it crosses that point, then the force from the spring is going to be bigger. So this is why on the way up, gravity is bigger. We cross that equilibrium point, we have negative acceleration. On the way down, we cross that point, gravity is bigger, then we're going to have negative acceleration, positive acceleration, depending on which one is bigger. Now, here's the next on question number 2. So, and again, this equation sheet, this is not on your equation sheet. So if you need this on the test, I will give you this equation, okay? So don't flip out, oh, I'm going to memorize that. No, don't. You just have to know how to use it.
What's before the equals sign?
It's on your sheet. It's on question number 2. Okay.
A function. My
So-
least favorite.
And for some reason, my pen is like real jerky, like it like skips a lot today. I don't know why. Maybe it's the cold weather. All right. So here's the deal. So you've got to have your Vmax from the previous page. Okay. So from that previous section, you've got to have your Vmax. So that's the calculation that you've already done. You have that number. So what we're trying to find now is what is the velocity as a function of time. So the Vmax equation is a one-trick pony. It's a good trick, okay? But it only calculates the velocity at that equilibrium point. What this equation allows you to do is calculate the velocity at any point. So this is like a function equation. So we can plug in any value of time and find the velocity at that instant, okay? That's what we're trying to figure out. Okay, what's the velocity at any given point in time? It's the function equation. Now, at this point, I'm going to tell you specifically which ones I want you to do. There's 2 ways that you can do this. I'm going to show you both. How you do this is up to you. One is smash mouth physics. The other one is a more elegant approach, okay? You pick whichever one fits best into your understanding of the process. Which one do you want to do first? Smash mouth, elegant. Elegant, okay.
Hey, now.
So on the more elegant approach, you're going to have negative Vmax times the sine of 2 pi. Now, on the first one, I'm going to have that as 0 over t. I don't know what t is. I don't care what t is. I just know that it's the period. So mathematically, and again, you have to be in radian mode. Okay, so if you're not confident about this, this is why God made calculators. If you're not confident about your trig functions, which some are and some aren't, basically, you're going to take the sine of 0. Okay? So when you take the sine of 0 in radian mode, what do you get? You get 1. Okay, you get 1. So if that's the case, then at time 0, are you sure you get 1?
You get 0.
You get 0. Okay?
Cosine, you get 1.
Cosine's 1. Cosine is 1.
You get 0. Okay?
We're smart here.
I know. That's okay. So here's the deal. So the sine of 0 is 0. So what this means is that at time 0, you're going to get a velocity of 0, which is why your velocity time graph starts at, oddly enough, 0. Okay? That's where you're at. Okay? This is why we have to define the system the way we do. So that's the elegant approach. You still get the same answer with the smash mouth physics. So like Cassidy, what did your group get for their value of period?
1.024 seconds.
1 point what?
0.24 seconds.
0.2? I call it 1.02 seconds. So if you want to do smash mouth physics and you're in Cassidy's group, you either take 0 divided by 1.02 seconds. Oddly enough, you're still going to get 0, and you're off to the races. You're still going to get a velocity of 0 at time 0. Now you want to go to a quarter t. So again, here's the 2 ways you can do this. So what do you have as your Vmax?
0.302.
0.302. Okay. So there's the significance of that negative sign. So you're going to take negative 0.302, which is that Vmax, times the sine. Now, this is the more elegant approach, okay? So that's going to be 2 pi times t over 4 divided by t. I'm not going to put in numbers. I don't care what the numbers are. I just know that this is going to be a quarter t. So when I take this, what's going to happen to my t's?
Cancel.
T is going to cancel out, right? So what I'm left with is 2 pi over 4, which reduces down to what?
Pi over 2.
Sine of pi over 2.
That's one.
There you go. So now, at this point, if you don't trust your trig functions, your knowledge of trig functions, you can take negative 3.02, make sure that you're in radian mode, times the sine of pi over 2. Okay? So like I said, this is a more elegant approach. The t's cancel out. You're just always left with dealing with some value of pi. So what do you get out of that answer of 1/4 t? You just get that maximum velocity. Oh, right. So that's why on your velocity time graph, at 1/4 t, this is when you're going to be down here with that biggest negative velocity. And that's the significance of that negative sign that's out in front of it. Now, if you don't like this, like, oh man, Burkhead, that's just going to get weird. We're like dropping out t's and all of this good stuff. Like, this is just weird. Okay, I like numbers. Fine. You like numbers. How are you going to find t over 4? If you're Cassidy's group and that period was 1.02 seconds, what are you going to put in there? So you're going to take, here's your smash mouth physics approach, times the sine of 2 pi. So Cassidy is going to take, what was it, 1.02 seconds? So she's going to take 1.02 seconds, divide that by 4, and then divide that by 1.02 seconds and take the sine of all of that. So if you hate, it's like, I hate variables. Then some people do. Some people just, I don't know why, they absolutely abhor working with variables. They want numbers. Okay, they hate variables. They want numbers. Fine. Take the period, divide it by 4, take the sine of 2 pi times that, divide it by that 1.02, you're still going to get the exact same answer. Okay? So I don't care how you do it. Just pick the one that makes the most sense to you. Okay? I don't care. Now, so you're back to 1/2 t. Okay. Again, go if you're the elegant approach, hey, I got negative 3.02 times the sine of 2 pi, and then I've got t over 2 divided by t. So the 2's cancel out, the t's cancel out. I've got the sine of pi. Okay? If you know your trig functions, you're taking the sine of pi, figure out what that is, boom, you're off to the races. Okay? So go ahead and do all those calculations for number 2, and then you can use that to answer to questions 3 and 4. And actually 3, 4, and 5. We'll talk about number 6. So finish those calculations, answer those questions, stop that camera.
Yeah, that's my bad.
That would have been bad.
Kind of
That would've been
animal.
Okay, so let's talk about this next equation, A max equals negative kx over mx. So this one's going to change depending upon what your k values are. So again, if you look at the units on this deal, you have that k value, which is newtons per meter, and then you have the mass, which is in kilograms, and then you have that x, which is like some position in meters. So if you go through all the mumbo jumbo, newtons are kilograms, meters per second squared, you end up with acceleration, which is what we want that A max to be. So this is going to change depending upon what you have. So clearly, if you look at this, then this is going to be whatever that amplitude is. Probably something around 0.05 meters, whatever this is. So if you think about it, to get that maximum acceleration, if you want a big acceleration, this isn't the velocity, okay? Listen to me. This is not the velocity. This is your acceleration. So if you want a big acceleration, you want to have a big spring constant with a small mass multiplied by a big amplitude, okay? That's what's going to create the biggest possible acceleration. And again, if you let x go to 0, oh, if you don't have any amplitude, guess what? You don't have any acceleration. So that's where this is going to play out. And if you don't have any mass, guess what? Your acceleration becomes undefined, which doesn't make any sense anyway, because you're going to try and make a spring oscillate with no mass on it, and that's just going to be weird anyway. So, plug and chug. Make sure I can see the work, because this one's going to change depending. This one's going to change a little bit with the different groups depending upon what your K value is. Okay. Mass is going to be the same for everybody. That's going to be that 1.5 kilograms. That's going to be that amplitude. That's going to get you that maximum acceleration. So when you get to number 8, so this is a little bit weird because of this negative sign out front, but it's going to be the same idea. So on number 8, you're going to find this acceleration. Yes, Evan?
On number 6, do you want us to use, for the position, do we want to use our measured one or the 0?
Whichever one you want to use. I don't care. Just make sure I know which one that you're using.
Okay.
Okay? So when you get to number 8, okay, this is a situation where you have an equation, but you have to look at it in terms of the physical reality of what's taking place in terms of how you've defined your system. Okay? So when you get to number 8, when you look at your acceleration time graph, at time 0, where's that acceleration? Is it a big positive value? Is it a big negative value? Or is it 0? At time 0, is your acceleration a big positive value, a big negative value, or is it 0? It's a big negative value, right? So when you look at your graph, okay, you have an equation, but you have to look at it in terms of how this system is being defined based upon this problem. So you know at time 0 you're going to have your biggest possible negative acceleration based upon how we define this system. So no matter what, at time 0 you're going to have some negative acceleration. So what you're going to do is you're going to have your A max, which is, and this is where this works out. So this is a negative of that A max, which is what you're going to get out of here, right? So that's going to be this negative value. And then you're going to have the sine of 2 pi t over t. And again, I don't care how you handle this. If you're a smash mouth physics person, you're going to put time 0 divided by 1.02 seconds or whatever that period is. If you want to work with variables and go, oh, that's just 0 divided by t, this whole thing becomes 0, I'm taking the cosine of 0. Now, what's the cosine of 0? 1. So at time 0, you're taking the cosine of 0, which is going to be 1. So guess what? Your acceleration at time 0 is going to be just a big negative value. Okay? So pay attention to the signs. So on number 8, basically, you're going to have some negative accelerations. You're going to have some 0 accelerations. You're going to have maybe 1 positive acceleration. Okay? Then when you get to number 9, indicate is the net force positive, negative, or 0. Well, look, F equals ma. Mass is always a positive value. So if you have negative acceleration, guess what? You're going to have a negative net force. Okay? So go ahead. Now at this point, when you get down to number 10, okay, this is on the velocity time graph, indicate the sign of the acceleration in each segment. Don't skip that. Okay? So you're going to go back to the velocity time graph. You go back to the velocity time graph and label the sign of the acceleration, positive or negative. Then on number 11, at times 1/4 t and t, on the velocity time graph, you're going to draw tangent lines. I want to see the tangent lines, okay? Draw them so that I can see them, okay? If I have to guess, like, did they draw the tangent lines or not? I'm not going to give you the benefit of the doubt, okay? Make sure that I can see those tangent lines, and then you're going to allow you to answer number 11. Don't worry about number 12. I've got a demo that I've got to set up for number 12. Okay? So you should at this point be able to work 8, 9, 10, and 11. So stop the under camera. Okay, kind of make sure that you can get this in the...
Zoom out. There we go.
Okay. So on number 12, we'll talk about the difference between what's called inertial mass
There you go,
and
Christian.
gravitational mass. Okay? So
And Adam.
let's say we happen to have our Newton scale, right? And we want to find what this particular mass weighs. Okay, that's kind of cool. We're on Earth, not a big deal. We have our scale, we zero it out, we hook it up, we get 1.96 newtons, which is what we should, because of the fact that it's a 0.2 kilogram mass. 0.2 times 9.8, we get 1.96 newtons. So we get the exact value that we predict that we should. But if you look at how this works because of the fact that this mass is interacting with the gravitational field of this rock that we're on, okay? So when you talk about gravitational values, you're talking about how that interacts with the gravitational field. We know, and we've calibrated this scale, so that we know if we put a 0.2 kilogram mass on the surface of the Earth, this scale should read 1.96 newtons, which is exactly what it reads. Now, if we take the same thing to the moon, okay, go to the moon, ultimate field trip, snap our fingers, boom, we're up. I hook this thing up on the moon. What's going to happen to the reading on the scale? It's going to be much less, right? It's going to be about, the gravitational acceleration on the moon is about 1.5, okay? So if you take like 0.2 times 1.5, you get about like 0.3. So if we were on the moon, this scale would be reading about 0.3 newtons. Oh, okay, cool. So as long as you have a gravitational field, you can use a scale like this. But the problem is that if you're in deep space, and there's no effective gravitational field, or if I'm in a state of free fall around the Earth, like I'm in orbit, like I'm on the International Space Station, okay? If I'm in the International Space Station and I'm in the state of free fall around the Earth, and I try and do this, okay, I won't get a reading. There's no way for me to use a gravitational field in a state of free fall around the Earth to find out how much this thing, what the mass of this object is. Because this won't do me any good, okay? It's worthless if I'm in a state of free fall or if I'm in zero gravitational field. So, what we can do is use this contraption. You're going, oh, this is kind of weird. So, this is basically, it's just two like flexible metal strands, and then there's like a hole in it, and I've got this slug that's in the middle of it. So basically, we can put this thing in there, and then we can begin to make it oscillate. Okay? So this is simple harmonic motion. So the beauty of this one is, because it's going back and forth, the only types of energy that we have, and this is going to play out large later on, the only types of energy that we have here are potential energy stored in the spring and kinetic energy. Because we're not oscillating up and down, we don't have to worry about UG. So in this situation, we're only going to have two types of energy, us and kinetic. We don't have to worry about UG. So this makes the calculations a little bit simpler. So if I want to figure out what this mass is, it's pretty simple, okay? So if you go back up to how you calculated the period of, you had period equals 2 pi times the square root of m over k. So all we have to do is get this thing oscillating back and forth, take a stopwatch, measure that period. Oh, now we'd have t. We'd have to know what the spring constant is for that setup. And if we knew that, then we can measure the mass. So if you're, and that's going to be important. So if we're going to Mars, or if you're in an extended stay in the International Space Station or in the state of orbit, we have to make sure that, hey, what are the astronauts doing? Okay, are they losing weight? Are they gaining weight? What are they doing? Well, the most worthless thing that you can pack along to take to the International Space Station is a bathroom scale. Why? It's not going to work. Okay, you stand on a bathroom scale in a state of free fall. Oh, I don't weigh anything. That's cool, right? Worthless. Don't take it. Won't do any good. On Earth, yeah, it works. So one option to try and find the mass is that you set up a situation like this. Oh, okay. If we know the value of the spring constant, we can measure the period, we know what 2 pi is, we can solve this equation for mass, we can figure out what's going to happen to the mass. Now, look at what's going to happen. This is with this slug. I'm going to put another 200 kilogram mass in there. What should happen to the period?
Increase.
Increase, decrease, or stay the same?
Increase.
Increase. Why?
Because it got bigger.
Yeah. Mathematically, I'm going to have a bigger mass, right? From an inertial standpoint, I'm going to have more mass. So it's going to be harder to get it to move, but once it's moving, it's harder to get it to stop. So if you visualize this, okay, there's that, okay? So now, put that on there. Now when I do that same thing, notice that that's noticeably smaller, okay? That period then has become bigger because of the fact that we have more mass included in the system. So if that's what you're using to figure out the mass of the astronauts, it's one option. You can sit there and go, okay, we can look at the influence of the period of that oscillation. Oh, if you're losing mass, oh, that period is going to become a smaller number. If I'm like, man, how'd you sneak a whole pack of Snickers onto the space station? Oh, I got a care package from home. Okay? So then if that mass is getting bigger, that period is going to become longer, right? It's like, oh man, what are you getting Snickers? Okay? Now, if we put even more mass on there, now what's going to happen?
More. It gets
Yeah,
bigger.
now it's like watching it in slow motion. Okay? So now, because we even have more mass on there, that period is going to become longer. Now, as that period is becoming longer, what's happening to the frequency?
becomes
It's becoming less and less and less.
less. Yeah.
So I'm going to have fewer oscillations because it's going to take longer for each one. So now, if we take everything off, and now I do it, okay? So now the mass is really, really small. So now I have a very small mass. So what's going to happen to the period? It's going to become
Smaller.
so the frequency is going to go up, and now we're going to vibrate really, really quickly. Okay? So this I could use on the moon, I could use on Earth, I could use in the International Space Station. Because, and here's the difference between inertial mass and gravitational. Gravitational mass is depending upon the interaction with a gravitational field. Inertial mass is just based upon how much, it's a highly technical term, how much stuff there is. And you can measure the influence that it has, like on a spring or something that's about to oscillate. Okay, so that's basically your answer to number 12. So, if you flip the page over, let's talk about question number 13. So there's a couple of caveats that's going to happen on question number 13. So we're going to the International Space Station. I don't know what's going to happen when we shut down the International Space Station. Hopefully something else will take its place. So, you want to determine the inertial mass of a block of iron. Describe how you can determine the inertial block of the mass, assuming that, now listen to what you have. Listen to what you have. You have a spring with a known spring constant, okay? Be specific about what you would measure and the equations you would use. So when you answer question number 13, I want to see an equation, okay? I want to see an equation. And you're going to say, hey, I'm going to solve for this variable, but I'm going to measure this, okay? So that's how you want to approach question number 13. You're going to say, I'm going to solve for this. Out of this equation, I'm going to measure this. That's what's going to allow me to calculate the value of mass. When you get to question number 14, okay? However, we forgot the spring. It's like, oh, really? We get all the way here, and you had one job. Pack the spring. What did you not do? Pack the spring. However, you have a force sensor like this. Okay? You have a force sensor. So, here's what I want you to think through on number 14. I still want to find the mass of the block. You have a force sensor. So what could you measure?
Force.
Maybe, I'm just throwing that out there. Okay, maybe we could measure force, right? So that's an option. Now, here's what's important. You also have a meter stick. You have a meter stick. You also have a stopwatch. Right. Okay. Got a force sensor, got a meter stick, stopwatch. Okay. From there, how could you use that equipment to determine the mass? And again, when you answer number 14, I tell you in the instructions, be specific about what you would measure and the equations you would use. Let me give you a hint. One of the equations is going to be F equals ma. Okay? That's going to be one of them that you're going to use. But the problem is you don't know what the acceleration is. But guess what? You can find the acceleration. So you're going to have to go old school kinematics and say, hey, we can measure this and this, and we can use that to find the acceleration. And then we can use that in F equals ma. Okay? So on number 13, what I'm looking for there is to tell me what equation you're going to use, what are you going to solve for, what are you going to measure, and how are you going to use that to find the mass. On 14, it's a little bit more complicated. You had to use two equations, one of them being F equals ma. How are you going to use that to find the mass? So when you get to, that's going to allow you to get to answer 13 and 14, and we'll talk about 15, 16, and 17 in just a second. So stop that, answer question 13 and 14. The yellow sheet kind of blends in with your hoodie. Literally from here, it just looks indistinguishable.
So photogenic.
Whatever. Okay, so let me talk, this is going to segue into tomorrow as well. So when you're talking about number 15, let me kind of give you this visual. So you all are used to having springs like oscillate vertically in a gravitational field. So imagine that you're going to have a spring, on the end of that is going to be a mass, but instead of oscillating vertically, we're going to have it oscillate horizontally with, and we don't have that, just like this, then we don't have to worry about any gravitational potential energy. We don't have to worry about us. So, if you consider like that being that equilibrium position, when it's at its maximum displacement, okay, this is going to be the key. When it's at its maximum displacement, that's going to be that amplitude, okay? That's going to be your amplitude. So if you look at us being 1/2 kx squared, that's the generic way that you can calculate any potential energy stored as us. Well, if you're at the equilibrium position, what's the value of x going to be?
0.
0. Guess what? How much us are you going to have?
0.
None. You're not going to have any us, right? Because x is going to be 0.
There is no us.
When it's at its maximum, either compression or elongation, what are you going to use for the value of x? The amplitude, right? Because that's that amplitude, which is that displacement from the equilibrium point. So if you're at that equilibrium point, you have no us. Guess what? All that energy is going to be kinetic. So if x equals 0, us is going to equal to 0. You're going to have all kinetic energy. When you're at either side of the amplitudes, okay, when you're at either side of the amplitudes, when you're at the other extreme, what's your velocity going to equal?
0.
0. Why?
Because it's slowing down.
Yeah, and you're going to change direction. Slow down, stop, speed back up.
Yeah.
So if you're at your maximum, us then is going to equal 1/2 k amplitude squared. Okay? So don't look at this and go, oh, there's a new equation. No, it's just 1/2 kx squared. But when you're at a maximum compression or elongation, that x is going to be that amplitude. So here's the deal. Your us plus your kinetic energy together are always going to add up to equal some constant. Now, we don't have to worry about because we're not oscillating vertically. Don't worry about this. So basically, what we can say here is that when we're at the middle, when it's at that equilibrium point, we have no us. All the energy is going to be kinetic. When we're at one of the extremes, we have no kinetic, and the potential energy we can find by taking 1/2 ka squared. So it's either all kinetic in the middle. The other extremes is that it's all going to be us. Now, in between, these two values are still going to add up to whatever that constant is. So if we know, and this is where this whole idea of conservation of energy, you all have done problems like this. Oh, right, the spring is partially released. Oh, right, we're going to have a certain amount of us, and we're going to have a certain amount of kinetic energy, and those values are still going to add up to equal whatever that constant is. So, by tomorrow, here's the only thing you have to have done by tomorrow, is get through 17 on the back side of that page. We'll deal with the rest of the assignment tomorrow in class. Okay? So you don't have any homework tonight. We're just going to finish this up tomorrow. Okay?
Let's go.